So what does this sampling distribution look like? Well, let's imagine this. You take a sample. Let's imagine we are looking at, for adults in Davis, California, heights and weights, right? So if I go out and take a sample of N, whether N is, 13 people or 100 people, get heights and weights, make a scatter plot, get a regression slope. If I do that, and you do that, and somebody else does that, and lots and lots and lots and lots of us do that, and if we then plot those different B's that we get, you get a distribution that's going to look like this. Approximately normal, centered around the true population regression value of beta 1. That's handy. So the center of our B1, our sample slope distribution, is the true regression slope for the entire population. Now the standard deviation, look at this, it's a little bit complicated. It depends on 2 standard deviations and 1 sample size. Now, I hope this makes sense. We've seen this square root of n thing before. So as your sample size goes up, what happens is your standard deviation goes down. You have more good data, less variability in the result. Now, the 2 sigmas here are different. On the bottom is the sigma x. That's just how spread out our x's are. So in the case of the height and weight example, it would be saying, do we have heights that go from short to tall? Are they very spread out? Big sigma x. Are all the heights we got kind of close together? Little sigma x. And the larger that is, the lower the variability in the slopes, which I hope makes a little bit of sense. Imagine this. If you've got some data points that are all real close together, well, then there's a whole lot of lines that might make sense, right? But if you've got data points that are super spread out, well, now there are fewer options that make sense, and they're all a little bit closer together. So that's what's happening there with the sigma x on the bottom. Now, the sigma on top, that's the S we've talked about before. It's the standard error of the residuals. If that's big, then sigma B1 is big. If that's small, then sigma B1 is small. That's for this reason. If you've got points that are really all very close to a line, well, then guess what? You've got a pretty good idea what the slope of that line is. So if this is small, so is the variability among our sample slopes. However, if your points are super spread out, then again, there are different possibilities that could possibly make some sense. You're going to have more variability in what you get as your sample slopes as you work through. So that's the structure of this formula. Now let's turn it into how we actually do calculations, because in reality, we don't know this. This is a population standard deviation of residuals, which we don't have. This is a population standard deviation of x values, which we don't have. So we instead are going to use standard errors. We're going to approximate sigmas with s's. So standard deviation of the residuals, standard deviation of the x's, sample standard deviations. And notice at the end just turns into an n-1. So in both the standardized test stat and the confidence interval, this standard error of statistic is this. That's that right there. We're generally going to rely on computers and calculators to find that for us. Here's the thing I need you to know, though. We're going to use the t distribution, because remember, we had something that was roughly normal, kind of like we do with means, and we use t's for means. We're going to use t's here. But the degrees of freedom is n-2. n-2, where n is the number of points, xy pairs, that you used to find that sample slope. So going forward, here from your formula sheets is the important standard error, and we need to remember we're using a t distribution with n-2 degrees of freedom. The way that I remember that is that ordered pairs have 2 numbers in them, an x and a y.